Now, as mentioned, thermodynamics is the science of energy and entropy, in particular the conversion of energy. Now, energy is broken down into three components. The first is internal energy, represented by the variable capital U, and this has units of joules. Internal energy is the energy contained within our system, and it's strongly a function of temperature and pressure. Now, it's all the energy in our system excluding the following. Kinetic energy, which is represented by the variable Ke, also has units of joules. Now, kinetic energy is the energy of motion. For translational motion, your kinetic energy is 1/2 mv squared. Potential energy, represented by the variable Pe, has units of joules as well. And this is the energy due to external force fields, such as a gravitational force field. Now, our total energy, E, is equal to the sum of our internal energy, our kinetic energy, and our potential energy. Our unit of energy is joules, which is a Newton meter, or represented in base units is kilograms meter squared per second squared. And this is equivalent to the energy transferred to an object when a force of 1 Newton acts on this object in the direction of its motion through a distance of 1 meter. Now, specific energy is just our energy on a per mass basis, and we represent this with a lowercase e. Our specific energy is equal to our specific internal energy, which is represented by lowercase u, plus our specific kinetic energy, which is represented by lowercase ke, plus our specific potential energy, which is represented by pe. And this would be equal to u plus v squared per 2 plus gz. Notice how there is no mass dependence. It is noted that our kinetic energy in this formulation is for translational energy. We can modify this easily for other forms of motion, such as rotational motion. The energy we are interested in a macroscopic viewpoint is always taken in reference to a basal value. For u, our specific internal energy is very difficult to quantify. When we begin to work with the thermodynamic steam tables, we will see that our reference point is often taken such that u at that reference point is equal to 0. Now, our units for our specific energy is kilojoule per kg. What we have to note is that each term on the right-hand side of our expression for our specific energy has to obey homogeneity. Now let us look at a situation where we have a copper block that has a specific internal energy of 1 kilojoule per kg, and it is moving horizontally across the surface with a velocity of 25 meters per second. We want to determine our total specific energy. Neglecting potential energy, since no information was given about any reference elevation, our specific energy is equal to our specific internal energy, lowercase u, plus our specific kinetic energy, v squared per 2. Now our specific internal energy is 1 kilojoule per kg. Our velocity is 25 meters per second. If we square this, we'd have 25 squared meters squared per second squared, divided by 2. Now these units do not match that of our specific internal energy. Thus we have to do the conversion of 1000 meters squared per second squared being equal to 1 kilojoule per kg. In doing such, we obey homogeneity between our specific internal energy and our specific kinetic energy. Thus, our total specific energy E is equal to 1.3125 kilojoule per kg.